Hello, ladies and gentlemen. Today we're going to be talking about the distance formula and how it relates to things that you already know. So the goal today is how to find the distance between 2 points, whether that's given to us on a graph or whether that's given to us by just the ordered pairs or the coordinates of those points. So our essential question today is just that. How do I find the distance between 2 points? Remember, you can always find the essential question if I forget in my videos, in my future videos. You can always find the essential question by looking at those I can statements on your unit dividers. And then instead of saying I can do this, you would say, how do I do this? And that's where my essential questions come from. With that, let's get started. Remember, if there's no pencil in the top right-hand corner, this is a part of the video where you just listen. You simply listen and you don't necessarily need to write anything down quite yet. So when we find distance on a coordinate plane, it can be really easy when our ordered pairs line up so that it's a vertical distance, like from B to C, or a horizontal distance from like A to B. So if we just count from A to B, we have 1, 2, 3, 4, 5, 6 units on a graph. And from B to C, we have 1, 2, 3 units. It gets a little trickier when we have to go across those grids and count diagonally, if you will. We can't count like that because the distance between here and here is going to be different between the distance from here to here. So how we've done that in the past, and maybe in your previous math classes, is you used a theorem called the Pythagorean theorem, where you said a squared plus b squared is equal to c squared. And that c squared value would be your hypotenuse, or the side across from the 90-degree angle. So in that case, A and B are just the legs of the right triangle, which could be 3 squared plus 6 squared, or you could have flipped them around and said 6 squared plus 3 squared. But either way, that's how you found distance in the past. What if we take away the graph, though? That's what we're trying to figure out. So if we don't have the grids and we don't count, there's still a way for us to go and find, it's a formula, it's called the distance formula, to get that diagonal distance, whether we're just given the ordered pairs or once we don't have those grids to count with the Pythagorean theorem. And here it is, the distance formula. Let's bring the connection together. So hopefully you have the formula written down. If not, then you can write that down. But if we were to make our right triangle and bring it back to what we know with Pythagorean theorem, we know that a squared plus b squared will be equal to our c squared distance. So instead of calling them A, B, and C, let's call them the difference between the x values. So if you look from like here to here, that's how I got x2 minus x1, is the ordered pair on x2 and x1, that x value of those two ordered pairs. The difference of that, I'm squaring that, and that's my a squared. Plus the difference in my y squareds now, when I go up and down, I'm taking that y2 coordinate from my second point minus my y value of that first coordinate, and that's how I got b squared. And typically that would all be equal to c squared, and they're just taking a shortcut by saying, let's find c right away, and this is what it would be. So the distance formula looks like a long, complicated formula like d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. All it comes down to is the difference in your x values and the difference in your y values, and that's all ultimately coming back, or it's derived from that Pythagorean theorem. So let's look at some examples. So we're always going to start with d is equal to the square root, and we're going to do x2 and x1. It doesn't matter if you label this point as 1 and this point as 2, or vice versa. Just make sure you know which ordered pair you're starting with versus which ordered pair you're not starting with. So I'm going to label them x comma y because that's our coordinates, and then my first ordered pair is going to be -2, -1, and my second ordered pair is going to be 4, 5. So it would be 4 minus a -2 for my x, the difference in my x's, plus 5 minus a -1. Oops, my pen glitched out, sorry about that. If we have a minus A negative, that changes to a positive, 4 plus 2 is 6 squared. 5 plus 1 is 6 squared. We have d is equal to that. 6 squared is 36. 36. In your notes, you should have to keep your answers in simplest radical form. 36 plus 36 is 72. So rather than punching this into your calculator and giving me a decimal, we want to break it up into perfect squares. We know 36 can go into 72, right? Because we just did that. So it'd be 36 times 2. I'm running out of room, so my final answer, wrong. 6 square roots of 2 is your final answer in simplest radical form. Okay, let's try another one. Again, you could label this as your first or your second order pair, and this is your first order pair. It doesn't matter, as long as you take the difference between the x's and the difference between the y's. So we'd have negative 4 minus 0 squared for the difference in my x's, plus 2 minus a negative 8 squared. Negative 4 minus 0 is a negative 4. We're going to square that, plus 2 minus a negative is going to change it to a plus again. So that would be 10 squared, taking the square root of that. Negative 4 squared. We want to make sure to keep the parentheses because we don't want to have any negatives under the under the radical sign. So negative 4 squared is a positive 16, plus 10 squared is 100. We're left with breaking down the radical, the square root of 116. If you need to think back to how to break up radicals under, or numbers underneath a radical, how to keep it in simplest radical form, you have to come up with your list of perfect squares. I'll put them over here. So like 1, 4, 9, 16, 25, 36, and so on and so forth. Any number squared is a perfect squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. I think you get the pattern. You have to figure out if any of these perfect squared numbers go into or factor into 116. And we do have one. We have 4 and 29. We can break down the square root of 4 into 2. We can't break down the square root of 29 any further. So that would be our final answer for number 2. Okay, last 2 examples for today. Let's see if we can hammer them out here really quick. So the difference in my x's, again, it doesn't matter if you start with the first order pair or the second order pair, just know which one you're labeling as order pair 1 or 2. So 4 minus 0 squared for my x's, plus negative 6 minus 3 squared. I'm going to have 4 squared plus a negative 9 squared. Remember, our answer should be, or when we square these things, they should stay positive. So 4 squared is 16, plus 9 squared is 81. Take the square root of that. 16 plus 81 is 97. There are no perfect squares that go into 97, so that would be your final answer for number 3. Moving on to number 4. Take the difference in your x's. Again, you could start with that second order pair, 4 minus a negative 4 squared, plus 3 minus a negative 3 squared. Those would change to plus signs when you do minus a negative. 4 plus 4 is 8. 3 plus 3 is 6. 8 squared is 64. 6 squared is 36. 64 plus 36 is 100. What happens when you have the square root of a perfect square is that it comes out to a whole number, which would just be 10, because we know that 10 squared is 100. So if we undo that and go in the reverse order and take the square root of 100, we're left with a whole number, 10. Okay, I want to thank you all for taking good notes, and I'll see you soon.